So I want to talk about something that is really interesting, and I have to say I'm really excited about this research. And I'm not just saying this because it's a talk and everybody's introducing the topic with like, I'm so excited. It's exciting because it's about peer review, and this is something that we deal with all the time and that most of us actually don't like. At least this is my perception of how this. And before I kind of talk about what we have been doing and why this is relevant to security and why this is relevant to machine learning, I have to say that, of course, I didn't do much in this work, but instead there was a very powerful team, and most importantly, Thorsten and Erwin, and therefore I have them on the very first slide. And they have been kind of running this, and I think this whole project ended in a paper, which is great, but it took about 2 years, and that's far too long for a paper, to be honest. But it's great work, and so I'm happy to present it to you. And we need to start with a very short introduction to what actually is automatic paper reviewer assignment. I guess you all have a feeling what this is, and I will tell you what this is, and you will say yes, of course. First of all, what is peer review? In theory, the idea of peer review is that you have some kind of quality assurance, that you can kind of decide what kind of scientific contribution is worth being presented at a conference or published in a journal, and what kind of publication needs to go through multiple steps and so on and so forth. And we all know that this doesn't work, but in theory, there should be reviewers, and they are experts, and then there are submissions from you and from me, and these submissions are assigned to reviewers that have special expertise in the topic of our papers. Yeah, so if I write a paper about X, I would expect there's a reviewer or multiple reviewers, and they are also experts in X, and then they look at the paper and say, great work. Yeah, this is how it should be, and the process where this kind of matching happens is called paper reviewer assignment. Now, traditionally, maybe 20 years ago or 50 years ago or 100 years ago, this was a manual process. So there was something like a journal editor or program committee chair. And this person was manually going through the submissions, looking at the reviewers that were invited into the conference or invited into the journal, and then trying to find the best match from the submissions to the papers. Of course, this doesn't scale very well. And what we have in security nowadays is mainly bidding. And bidding means that the reviewers, they get a list of all the submissions, and then they can place bids on these submissions. So they can say, yeah, I want to review this paper, I want to review that paper, but I don't want to review this one here. And then there's some kind of fancy automatic assignment process. I think it builds on the Hungarian algorithm, but that's not the topic from this talk. But it's also interesting optimization-wise. And in many security conferences, it works exactly like this. Yeah? So if you submit to the top conferences in this field, I guess you do, this is how it is done. Now, there's not only security, which is likely the most important topic of research, but there's also other topics, and one being machine learning and computer vision. And these are 3 conferences that are very popular in machine learning and computer vision. And what you see on the graph is the number of submissions to the conferences per year. And when I plotted this, I was really surprised by how large these numbers are. We have written this in the paper, but I must admit, I never looked the numbers up myself until I did this plot. And I was surprised to see that there's like over 10,000 submissions for NeurIPS in 2022. Can you imagine 10,000 papers? And they all got submitted to the conference, and now they need to do a paper reviewer matching. Of course, the idea of bidding doesn't work anymore. I did a small calculation. So if I would take 3 seconds to read the title of the paper, yeah, and I think 3 seconds is kind of okay, it would take me 8 hours to go through this long list of submissions, and I wouldn't even have bid at this point. I would just have read out the titles aloud, and this would take a full workday. So it's clear that this kind of semi-automatic also doesn't work. If you wonder about security, can you see this light blue bar here? This is where we are currently in terms of impact. But I see, at least I would say that some of the conferences go up to this point, so have more than 1,000, 2,000 submissions. I'm sure that we will sooner or later run into the very same situation also for computer security, that manual bidding doesn't scale. Now, machine learning people have noticed this already 10 years ago, and they proposed in 2010 the first solution for automatic paper-to-reviewer assignment. And the reason they proposed this is that they are machine learning people, and when you give them a problem that is solved manually, they will always start to think about, can I solve this with one of my fancy machine learning algorithms? As a side note, in machine learning research, very often people already have the solutions and then they are looking for problems. Yeah. And this could be, I'm not sure, could be a case where this happened. They had very fancy so-called topic models. I will tell you what this is. And it seemed like a perfect match here. And out of this, there developed two standards or two systems, TPMS and AutoBit. TPMS is the closed source original system. AutoBit is an open source variant of it. And this TPMS, Toronto Paper Matching System, has been integrated by Microsoft into their conference management system. First question, just who knows that Microsoft is running a conference management system? Okay, yeah, so in the security world, this is maybe surprising, but the large machine learning conferences are in fact run with the system. It's called CMT, Conference Management Toolkit. And it's one of these systems like EasyShare or HotCrab that enables you to kind of collect submissions, match submissions, assign reviews, and then kind of manage the whole process of reviewing. So, and what I said is that at the core of this idea of automatically matching the two parties is topic modeling. In simple words, I'm extracting the topics from the paper that is submitted. I extract somehow the topics from the reviewers, and then I match the topics. And I'm doing this completely automatically, so there's no human involved. And in the end, I get a matching from topic experts to topic papers. And let's shortly look at how this works to get a feeling whether this is interesting for security research or not. And yeah, to see what's going on. And I try to make it this in very simple steps and do not go too much into some technical details. So in principle, we start with a paper. And in the first step, what TPMS and other systems for this automatic assignment do is they partition the paper into words. Or now you would say tokens, yeah, but originally this is more like back of words representation. And then you map them to some vector space. And in this vector space, each of the axes corresponds to one of the words. It's a classic representation from the 70s. And in this example here, this paper would contain the word code 76 times. So this is the frequency of the word. The word method would maybe appear 61 times, but the word crypto does not appear in this particular paper. And you can take this approach for every possible paper and generate such a vector representation from the paper. And it's clear at this point, you are throwing away a lot of the grammatical and syntactical structure of the text. So we are not looking at how the sentences are formed. We're not looking at how adverbs and nouns go with each other and things like that. Instead, we just look at the words. It's a very simple representation. And I also have to mention, people throw away so-called stop words. So words like off, for, we, paper, no, paper not maybe, but this and in, so that only the essence in terms of words remains. And then these topic models have the idea that if there is a topic in a paper, it is a recurring set of words. Yeah, so if you should talk about fruit salad, so let's say your paper's about fruit salad, you will always talk about apples and pears and things like that. Whereas if you talk about something else, how to make popcorn, there will be very less of these fruits, but there might be other patterns of words that occur very often, like popcorn and hot oil or whatever, what you need to make this. So, and we assume now, if we go to the security world, that if there's a paper about cryptography, likely very often there's the word crypto or maybe key or scheme and things like that. There exist several different algorithms that can extract these patterns. frequent one is LDA, but I'm not going to bore you with how this works. The core idea is the following. These vectors that I have, these papers, are moved to another space, which is called the topic space. And in this topic space, you represent a paper by the mixture of the contained topics. And to explain this, the idea is that a paper does not contain only one topic, but actually multiple topics. And so your paper becomes a mixture of these topics. Maybe it's 90% intrusion detection, 5% machine learning, and 4% fuzzing. I don't know how you got the fuzzing into this paper, but theoretically this should be possible. And then there's a long tail of 0 values, all of these topics that your paper does not touch. And so then we get this nice, funky little space where we can have a mixture of attack and model. This is maybe the attack space. This is the code analysis world. This is the crypto world. And now all our papers live within this topic space. And we can use this very technique to do paper to reviewer matching. And how do we do this? The first thing is we take the paper and map it into the space exactly as I described. So here's the paper. It contains 10% crypto, 20% attacks, and 70% code analysis. No idea what kind of paper this could be, but this is the example. And then I take the papers that have been written by the reviewers, so that they wrote in the past, and I put all of them together into a large archive. So this is the 20 most important papers. And then I put also these papers into the space as a vector for the reviewer. So this means then that a reviewer here with a circle dot also gets some point in this space. And maybe this reviewer has crypto attack analysis also as topics, but in a different mixture. And eventually I can do this for all my reviewers that are in my set that should be assigned to papers. And I can just compute distances and assign the reviewers based on distances in the topic space. So here, this reviewer, this reviewer, this reviewer, they are closer than all the others. So they would be assigned because they live closer in the topic space. Yeah. And I prepared two Darmstadt-like examples. It wasn't so easy because we have a list of many security people, but unfortunately not of everybody. So I had to search for some that I thought could be in Darmstadt. This is Ahmad and Sebastian Faust. And these are real computations from their papers because we did a simulation of a real conference. And although the topics are not perfect, I think they convey a little bit that there's really information contained in these co-occurrent words. So for example, Ahmad has secure hardware system, memory, software. I think this is a good topic. Enclave, SGX, secure execution data. This is all this trusted execution thing. And then model, backdoor attack, cluster dataset. I would assume this is more recent work. Or Sebastian more on the formal side, something with coin, contract, verification, hash. This is likely blockchain work. Or proof, compute, random, simulation, polynomial, and so on and so forth. So these models, although very simple, are capable of describing what researchers are doing. And they are also, at least when just looking at these 3 examples, at these 3 topics here, capture a little bit of what's going on. Okay, great. I'm not sure if you know it, but there were 2 security conferences that also used this automatic assignment. This was once happening in Oakland, so IEEE, Security and Privacy, 2015, I think, and as an experiment. And it also happened with CCS in 2017, I think, also as an experiment. So this, what I'm telling you, is not completely fantasy, but there have been PC shares in our community that were experimenting with this automatic assignment. Of course, people could still bid, but they were checking maybe this is a way to go in the future. And when we looked at this for the first time, we said like, oh, cool, this is an application of machine learning. It is somehow in an area where we work in. We don't work in peer review, maybe a little bit, but we submit these papers all the time. And maybe we can craft an adversarial paper that selects its own reviewers. And this would be great because we could exclude someone we don't like, and we could include someone that we like. Of course, only hypothetically. This would be scientific misconduct, and of course should have, must have very severe consequences. And therefore, it's clear we never did this. But I can tell you, when we submitted the paper to the conference the first time, all 3 reviewers were like, why did I get this paper for review? I was bidding on it, but now I'm not so sure after reading. And then we had to write in the rebuttal, of course, we didn't play any tricks. This paper is not manipulated. It seemed that they were not so happy about this, also from the review scores. Okay, so what's the idea? The idea is we have a paper that we get. This is our paper, we have written it, and we want to make a very small amount of changes to it, not much. Yeah. So the idea is not to write a completely new paper, because this could always be done. The idea is that you have a paper on your favorite topic and you make very fine changes to it. And by doing this, you try to move in this space. And in principle, you could write this as an optimization problem. We also did this. So we are looking for the smallest change to the paper that moves it from here, let's say, to there. And the reason is that now the 3 reviewers that are assigned change. And in particular, this one is now left out, and this one is added. So by just moving in the space, we can select reviewers for inclusion or rejection. It's clear that we cannot arbitrarily remove and include someone, because they also have a relation to themselves. Yeah? So if you have 2 people close to each other and as reviewers, you cannot exclude this one and add this one because you're moving in the direction. But in theory, you could maybe get away from this green bubble, which is this very destructive community that you don't like, and move to the very friendly community at the bottom that will always accept your paper. And I guess you know that these communities exist a little bit. So there's more friendly subfields and not so friendly subfields in security, and also in all other disciplines. Okay, and then the true story here is that I had this idea long ago, like 2017, and then I gave it to a student as a bachelor thesis. Why? Because I thought, this is adversarial machine learning. There's a ton of papers on adversarial machine learning. So the student just needs to read a little bit of the papers, implement them, and we're done. And surprisingly, none of the approaches available worked. And even when we wrote the paper in 2022, there was no approach that would do this. Yeah, and even though Twitter or X and all the other social media are full of paper reporting, like we do this and that, but most of them are not suitable here. And there's 2 reasons. One reason is, do I have an animation? Yeah. One reason is, it doesn't help us to just move in the space. Most of the papers that you will read deal with computer vision, and in computer vision, moving in this space, or in this case, it's the pixel space, is already the attack. So you modify the image directly and you're done. But in our case, if we want to go here, we just get a mixture of topics. What's missing is the paper. And what is missing is the changes to our paper. Yeah. So if we want to have a little bit more fruit salad in our paper, we have to add the fruit salad to it. Yeah, so it doesn't automatically fall off from the vector. So there's mathematically speaking, there's no inverse function from this topic model back to the original paper. And the other thing is that we found out, let's say the hard way, if you make these changes in a paper, if you, for example, do it by hand, you say, okay, I'm writing just a little bit of text and let's see. You will notice that there's a lot of side effects. So if you want to go there, you might end up there, because you cannot just add words to a text. You have to add sentences, and these sentences have to be embedded in the context. You cannot just write in a paper, hey, let's talk about fruit salad, and then you kind of say this, there's apple and pears and things like that. This doesn't work. The reviewers will see it. So you have to kind of say, okay, if we talk about blockchain, then we also have to talk about fruit salad. And so you need to kind of create these bridges. Yeah. And if you do this, you automatically introduce side effects, other words, and they move you into directions that you cannot control. And we had the idea that we want to tackle this, but it turns out it's not so easy. And we ended up with an approach that alternates between these two views. And formally, it looks like this. So here we make small steps. So we don't go directly to our target location, even though we know the target location. But instead of going there directly, we say, okay, let's maybe try this one. And then we make a stochastic process. So we also try this one and try this one. And from the K candidates, we select the best one for our next step. So we iteratively move in the topic space. And in each step, we try or we implement transformations of the paper that change certain words or certain content or certain formatting, just trying to accomplish these small steps, not the big steps. Yeah? So this could be the fruit salad example here, that I just want to add the word apple to a paper. And in this example, adding apple to a security paper is not so difficult, by the way. Yeah? You can say it works on Apple Mac, and then you have it. So the idea is to make small steps and move forward. And because I'm a funny person, I noticed that this algorithm can also be described differently. And I am sure that you don't know Sommerhaus der Stars. This was a trash TV series in 2018. You haven't seen it, I know. But there was one game that was exactly like our algorithm works. It's at the core the same algorithm. So the idea was that in this game, couples had to drive a car and they had to park the car. But the problem was the driver was blinded, and only the person next to the driver, the partner, could explain how to drive. And in principle, this is exactly how our algorithm works. So the driver is this search in the topic space, and the driver says like, well, no, wait, no, sorry, this is the navigator. That's the navigator is working in the topic space, and the navigator says like, you need to add this and that word. And the driver is steering, and steering means like adding, for example, a new sentence or making a modification to a table or making a modification to a reference. And then the navigator looks again at the paper and says like, oh, you added this, but we are too far to the left now, so steer back to the right. And then it goes back and forth between the two until they reach the parking lot. Exactly like this happened in the game. So let's talk a little bit about these two steps in more detail and understand what they do. I think the beam search, so the search in the topic space, is the easiest step. What we do is we know where we want to go, so we randomly sample from these words that are in there. We respect the probability, so it's not too complicated. There's just two things that we need to keep in mind, and these are modeled as constraints on the movement. One is an L1 constraint, so this means we want to have the total number of modified words to be small. So if we move, we do not want to move farther than 10 words, for example. This means at most 10 words are changed. And the other one is a constraint on the total modifications per word. So even if we only want to change one word, we do not want to include it 100 times. This is also not possible. So one of these constraints restricts the length of the movement in the L1 norm and the other one in the L infinity norm. And mathematically, this can be very nicely fit into an optimization problem, and it's technically not so complicated. And then we perform case steps under these constraints. And for each of these case steps, we ask the driver to see how he or she is driving there. And then after we have done this K new locations, we proceed again and move forward. So how do we change the document? And interestingly, I had the idea that always the text should be changed, the words, and I was thinking of very complicated modifications. And now with ChatGPT, I think that most of you also would have this in mind, like rephrasing the text, changing words and things like that. But my PhD students, they came up with dirty tricks. So they said, yes, we managed to solve the problem, but we didn't do it as you expected. We were trying PDF tricks on your document. And then I said, well, this dirty tricks, that's not allowed. but it turned out to be extremely effective. And in some cases where text changes were not possible, PDF tricks were always working. So we included both of these in our paper. So we have two sets of transformations, one being dirty tricks, or you can say changes of the format and encoding, and the others are true text form transformations. So let's look at some of these. The first thing that my PhD students noticed, I didn't know this, PDF is a very powerful format, and it has so-called accessibility features. So for example, if people that are vision impaired or blind get a PDF document, they can read the document because there's tools that can read out aloud the text from the PDF, which is great. And even better, you can have special features that explain something that is only seen visually. Yeah, so you can add these alternate texts to your document, and you can say this image shows this and that, or you can say this equation looks like that. And people that are blind, they can use this additional information. It's a great feature. Now, unfortunately, when you process a PDF document and you extract the text, guess which of these two representations is used? Is the visual version used, or is more the accessibility version used? Of course, the accessibility version is first because this needs to be processed further, for example, to be spoken by a speech synthesizer. So you can just attach other words to some words. So you can say, instead of having static and program here, we have crypto and analysis here. And once this is passed with a PDF parser, we tried different one and it worked. In all cases, you get crypto and analysis as output. And you can have multiple words here, and you can even remove words by replacing them with an empty string. So this is a technique that you can use to arbitrarily change the content. And I mean, at this point, actually, it's game over. But because we wanted to do more research and not just present some hacks, we did more. So some other thing that you can do in case this feature is disabled, you can use homoglyphs. And when I know homoglyphs as a security threat from phishing campaigns. So you have characters that look very similar to other characters, and then they are included in a host name, or they are included somewhere else, and people then confuse these characters. And I always thought, maybe because I'm a security researcher, that these homoglyphs look slightly the same. But of course, if I would look, I would immediately see it. Yeah. I would think this is like this French C or something with this small thing on the bottom. And of course, I would immediately see it. Yeah. Now I have something for you here just to make you interested. So this is an A, and this is a Cyrillic A. And unfortunately, the Cyrillic alphabet is not mapped to the Latin alphabet for those characters that are identical, but instead there's an identical copy of the character in UTF, whatever this is, Unicode representation. So these are two characters for the machine, but for a human, there's not even a pixel difference. So you can, if you see an A, the truth is you can never know whether it's a Cyrillic A or a Latin A. And there's many others of these dirty tricks. And of course, you can use them to remove words, because here static and program are not present anymore. This is a new word that contains a Cyrillic A at this position. But let's try to do it a little bit more advanced. So let's try to use all of this fancy machine learning that we are attacking ourselves as adversary and try to really change the text in the papers. One thing that we did is we used so-called word embedding. So who knows what a word embedding is? Very few. So this is a technique that is also, I would say, now 7 years old or so. So it's not super new, but it's very powerful. The idea is that you are learning a vector space. In this vector space, the vectors correspond to individual words. And by some magic, related words are close to those that you are looking at. Yeah? So this means if you have some adjectives in there, then you will find synonyms next to it. So there's good, next to good is also brilliant or excellent or whatever. And this works with all topics. and all content, so it's not restricted to certain types of words. So what we did is we just downloaded 11,000 security papers from arXiv and threw them into this algorithm and learned a word embedding of security terms. So then you can take a word from the security context and you get synonyms for it. And you can use this, for example, to change intrusion detection to attack identification. And I guess we all know that this might look like the similar terms, but for researchers, intrusion detection is like a fixed term. Attack identification is something we don't know. Or you can translate x86 binary into i386 software, which is also not completely matching, but the content or the semantics do not really change. And if you would review the paper, you would not assume that something evil is going on. You might think that these people maybe are a little bit strange, or I don't know. But what's happening here is that you are able to remove fixed keywords from your text. So in the automatic topic matching now, people that are experts in intrusion detection and x86 analysis, they will not be assigned to your paper anymore because you removed these words from your paper. And then we discovered another very cool thing, and this by accident. We found out that once we had crawled all these papers, we could also automatically add references to the paper. And I guess your advisor told you you can never have too many references. You can always add one or two. It doesn't hurt. And so we found out that many of the references alone already contain very good words, especially if we want to move in the direction of a certain topic. So for example, if we want to move into the direction of crypto and model, we could add this paper from Jan Jurjens. I picked it because it contains crypto and model in the title. And whatever topic you have in mind, I'm sure that within these 11,000 papers, there are some examples that fit exactly what you need. Yeah. Even maybe there's even something with apple and salad in it, or fruit salad, I don't know. And you can also have multiple references, and it will not really hurt, and it will be totally insuspicious. Who will complain that your paper has cited too many references? I haven't seen this complaint so far. And interestingly, often there are other terms that move into the right direction. So in this case, the side effect is to the advantage of the attacker. So for example, maybe also symbolic execution helps if you want to move in the direction of cryptographic models. I'm not sure, but potentially. So we found out that reference changes are very powerful. Then, of course, we had the idea that we can really generate completely text from scratch. And when we did this, this was before ChatGPT was published, and we were really proud of it. Nowadays, I would say it looks like it has been done 100 years ago in terms of technology. So we used this 350M, so this means 350 million parameter model. That's, I don't know, 10, I don't know. It's so small in comparison to what's the state of the art. I'm not even sure what the state of the art is today. So I'm refrain from making a characterization. So we used a very small open source language model, and we asked the language model to generate text containing specific words. And you know yourself, these models are extremely good in generating text. And if you ask them to include certain words, they will do this. So here we have an example that contains the word lip, lobe, inaudible, speaker, demod, and things like that. I didn't mention, by the way, that these approaches are not looking at complete words, but at stems. And maybe this confused you. So what's happening here is we are the topic models are working on stemmed words. What's the German? Wortstamm. So the idea is that instead of having inaudible, you just look at inaud. And by doing so, you capture a whole family of similar words. Yeah, or by demot, then you have demoted, demoting, and all of these other variations of the same word. And we did this, and it worked quite well. So we could generate some text, and if you read the text, it's okay. Yeah, but I think nowadays So a year later, it would work far better because there are far better language models now. And then we put all of this together and designed a system. And the only thing that is configurable is what we call an attack budget. Because if we would start this from scratch, it would use these dirty tricks all over the place and not use our sophisticated, smart academic things. So we said, okay, we want something like a budget the attacker has, and this budget defines how often certain tricks can be used. And we said you start with the less suspicious changes first. So something like you can have 10 synonyms added to the paper, you can add 10 references at most, you can generate at most 10 sentences, we have something like spelling mistakes, and then after, if these all have been used and you're still not at the position, then you can use the dirty tricks. And you start with, I think we start with the homoglyphs and use these accessibility features only at the very end, if we cannot succeed. So, and do I have an example? Wait. Yeah, here. So this is, let's look at the example. So this is a paper that we modified, and in blue, you can see the changes. It's a real paper, Johannes Kinder, I think, yes. And what's happening here, there's a lot of references added. Great. And here are some really, I mean, these are these synonym replacements. So for example, this paper is about, it's regularly talking about regex, so as a short for regular expressions. And this is replaced with RGX as an abbreviation for regex. It's super ugly, but it enables to completely remove or largely remove the term regular expression or regex from this paper, although it is about this topic. Yeah, it's and the changes make it like it's more about something called RGX. And there are other finer changes you can see here and there. A word is replaced to move in a certain direction. Why did we prepare this paper? Well, we prepared it because we wanted to do a real evaluation, not just some hypothetical thing, but we really want to simulate a conference and then see what's happening. And we simulated 2 conferences. I'm only showing the results for one. This is the IEEE Symposium, Security and Privacy 2020. And what does it mean to simulate the conference? Well, we looked at the homepage, identified the PC members, and then for each PC member, we downloaded the first 20 papers we found on their Google Scholar profile. And if they didn't have a Scholar profile, I think we removed them. And so we got a collection of reviewers that served on this particular conference. And then we needed papers from this conference with source code, because our modifications are made on the source code. When we did it, we had a couple of papers that were submitted to this conference. These were rejected papers from ourselves. But we thought maybe it would also make sense to look at papers that got accepted. So we went to archive and looked whether there are papers from this conference. And in total, we could collect 32 papers that were accepted at the conference. So these are real papers that went through the process and that are okay. So they are not like papers that are crap or broken already. They are perfect. This is one of the best conferences. So these, I would say, these are really strong papers. And then we simulated the conference and said, okay, we assign 5 reviewers from this group to each of these submissions, and then start from the original reviewers and then see how much can we change if we would be an author of this paper. And we did 2 types of attack, a white box attack and a black box attack. In the white box case, we assume that we know everything about how the system is trained. So we know exactly the papers that are used to train the topic model. And initially, we thought this is a reasonable assumption, but you will see on the next 2 slides, we need also the black box version where the attacker does not have exact knowledge of the topic model. So this is what a paper looks like. And then we started. And here you can see the outcome of the first white box result. So what we did is we found out that you cannot arbitrarily change people. So we cannot take someone who's working on usability and move them to a formal crypto paper. This would require too much changes. With our budget, we had this budget tuned, and you will see why we had this budget tuned. So we had this restricted budget, and then we said, okay, let's just look at the top 10 reviewers in our topic model. We know the top 5 have been selected. So let's play around with these 5 that have not been selected, which are close, and the 5 that have been selected, and see whether we can remove one of the top 5 to the other side and the other way around. And here, this is, I think, just the average over selection and rejection of reviewers. And in dark blue, you can see the attack success with only text changes. Encoding tricks, I didn't talk so much about it, is something like homoglyphs, and this other one is dirty tricks. And the summary message would be, after switching 16 times back and forth between the driver and the navigator, we end with 99% attack success. So we can arbitrarily select and reject from these top 10 reviewers. However, with only text changes, we can do this with only half of the papers. Yeah. So this means if you want to do this in practice, you shouldn't, but if you want to, you need to ask yourself, can I accept a 50% attack rate? So my paper maybe succeeds only in every second case. Or do I need this 99%? Then you have to make these format changes and play these dirty tricks. So then we were happy. And at some point, one of my students said, yeah, okay, let's try this, make it a little bit more realistic. So let's assume we do not exactly know how the topic model in the conference is trained, because maybe we don't have exactly the 20 papers from the reviewers. And this is realistic, I would say. I can look up your Google Scholar profiles, but I don't know exactly what papers have been used for training. And it turns out, in this plot, you can see it, if we do this, and we were looking at 70% match between the true papers and the attacker, then our attack rates drop to 60 or less than 40% instead of 99%. And we were a little bit sad, but then we noticed, okay, this is because our topic models contain non-determinism, so they are not always the same. But if we just remove one paper from it, they do not converge to the same state, but they converge slightly different. And then all of this doesn't work. And the solution was, instead of having just one topic model, we train 8 models. And we use only the 70%, but we kind of additionally leave out papers or add papers in so that we have these kind of variants captured in different versions. And then if we design a paper that exploits all of the 8 together, then this will also work on the target. Yeah, so we simulate a little bit the missing information by shuffling around what we have. Yeah. And yes, and then we again could go quite up to, again, over 80%. Then we were almost done. And then we found out that this randomness that I've been talking about, this is not only present on the attacker side, but unfortunately, this is also present on the conference side. So we found something strange, and I guess it's known in the machine learning community, but it wasn't known to us. If you train the model again on the very same data, you get different topic models. So in principle, this automatic assignment adds a lot of randomness to the assignment process. Yeah. And this means that if we have the same data and train 8 different topic models, so here we have these topic models, and now they correspond to the targets that we want to attack. Our attack, here these are papers that we prepared, does not always succeed. Blue means it succeeds. Light blue means it was already assigned to the reviewers anyway, so our attack was not necessary. And as you can see, there's a bunch of papers where our attack does not always succeed. And this means, as a bottom line, if you are doing this really in the reality and attacking a real conference management system, your chances are only 30% that your paper is assigned to the selected reviewers. Well, that's good. I think this is good news. But I must say, I was a little bit shocked that there's so much randomness in this process, because it means that if you submit your paper to the conference, and they train the model again on the very same data, you might get assigned to different reviewers. And this is not how it should be, at least in my understanding of how this works. Okay, so what's missing? Last slide on this part. We also asked people to look at these papers because we were afraid that maybe everybody would spot them. So we asked security researchers with a PhD to do mini reviews of the papers, and we asked them questions. And some got manipulated papers, others were in a control group. They didn't get these manipulated papers. And then the groups were switched so that everybody was looking at some point at manipulated and unmanipulated papers. And then we did a little bit of statistics. So for example, how do you rate the literature quality and bibliography? You remember that we added these, nobody noticed. So here these bars are identical. So it seems that people don't know how many references you should make. Or how do you rate the overall writing quality? I mean, these are papers accepted at the top conference. What I really like is this one here. This is the typical security reviewer. So these are accepted at Oakland, and there's one person that says they are all absolutely below quality. It's really completely worse. And this is the blue bar, unmodified. But I mean, there's a slight, you can see a little bit tendency that our modified papers are a little bit less high in quality, but still, this is on a Likert scale here. This is still, I don't know, medium to high. And if it comes, how likely is the paper manipulated by an automated system? They all say, let's say, unlikely. And interestingly, they also sometimes found unmodified papers suspicious. So this is this kind of problem of false positives, which also happens here. So they were not able to clearly differentiate our manipulations from regular papers. Okay, so brings me to the end and a little bit the aftermath. So what could we now do? So is there a solution to the problem? The first thing that I would highly recommend is that we get away from parsing these PDFs and analyzing the symbols in terms of Unicode or accessibility features. I would suggest to use OCR on the PDF. It sounds a little bit absurd, but this would guarantee that what as a human sees is in fact what is processed later, and it's not something else. And then, of course, there could be different detection strategies. So does your paper contain a lot of strange PDF features? But for the text transformations, I don't know how you can actually defend against this. We contacted the people who are running TPMS at Microsoft. We also contacted the developer of Autobit. It was a very fruitful email exchange, but at the end, they both said, we have very little time to put in these defenses, and researchers are honest. And there's, I think they were serious about this. And I think the security mindset is a little bit different, but they said, like, if somebody wants to game the system, they can do it anyway. So they will always do evil things. And it's true, of course. Yeah, they can do all sorts of other things. But personally, I would say this is still a threat because you don't need to always move completely to a certain selection of reviewers. It just helps to move your paper just a slight bit so that that likelihood of being assigned raises. And you can do this in a way that is currently not detectable. So if you go out of the talk, I don't know how to find out whether you are preparing your papers now with these techniques. I don't know how, so you can do it. Because I know you're honest. Yeah, this is important. Okay, and what's kind of the broader perspective? So what's the message? So what's interesting here is this is an attack that on the one end works in the classical adversarial machine learning domain where you have a vector space and you explore vulnerabilities in the learning model. But at the same time, you have an attack that operates in something that we very well understand, and this is text. And if you look at ChatGPT, there's some very recent research, but even people like Nicolas Carlini or Florian Trama, I'm not sure if you know them, but kind of the experts in the adversarial machine learning field, they are struggling with creating text that exploits vulnerabilities, because we as humans, we are we're very good in understanding text, and we notice if there's a strange word somewhere. So it's an interesting, we have a hybrid strategy. They tried on the direct way, and this seems to be very difficult. And I guess we will have a lot of fun with attacks on language models in the future. And lastly, and this is maybe for you that they are interested in doing research on learning and security, this system has been used for 13 years. And although there's like 10,000 papers on adversarial machine learning, nobody looked at it. And I bet if you look into other systems, for example, if you go to your industry partners and you say that, where are you using machine learning? Maybe they tell you about machine learning systems that are in place for 10 years where you can do attacks. So for example, I know there's I was once in a steel manufacturing plant, fabric, large super thing. And they had machine learning from the 90s trying to spot defects in the steel, whatever this was called. And I was also thinking, are there potential attacks that you can run to kind of artificially inject defects so that they would throw away certain steel? And because this is very expensive, it might be something to look at. Just as an example. I mean, I'm not in contact with them anymore. The group from Thorsten Holz set up a GitHub repository. So if you want to, you can look there. There's more papers, and there's also the entire code. So you can play around with this if you want to. Okay, so thanks.